I too prefer to speak in English for an obvious reason. I have no Italian. So if my English isn't clear enough, just shout at any point and I will go back and try and repeat anything that doesn't come across very well. The purpose of this case study is to investigate the phrase on the screen, I think, which is somewhat typical of many organisations. So we imagine that we've got a department in the UK MOD, the UK Army, called REME Aviation. Okay, what they do will become clear as we go through this talk. Now, REME Aviation consider that they are overstretched. Okay, so they think that they're working too hard. This particular department is working very hard indeed, anecdotally. However, the boss, AAC, consider that REME Aviation are over-resourced. So we've got two levels of the same organisation, okay? One that says, you can't take staff off me, I'm working very, 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 very hard indeed. However, the boss, the strategic manager, who's looking at his Excel dashboard, he's doing some analysis and he's saying, no, actually, you've got too many staff. I want to take 5% out of you next year. And I think this problem is probably typical of many large organisations where you've got people at the shop floor working very hard or seemingly and feeling like they're working very hard, and yet people at the very senior levels thinking, well, we can take 5–10% out of this according to the efficiency targets I might be meeting, or according to the efficiency of the equipment that's been promised by the company. I should be able to get more out of my factory or my purpose. So our particular project was to just investigate this trend, really.
I'm taking with
my name's obviously, I should have introduced myself. I'm Dave Buxton. I'm director of DSE Consulting. So DSE is the reseller of AnyLogic in the UK. I also have a second company. I'm greedy, obviously I want two consultancy companies, but I have a second consultancy called Decision Lab, for which I'm the head of simulation. So I'll try and explain a little bit more. So to give you a background for my company first, Decision Lab is still small enough to have all the pictures of everybody who works for us on the screen. So we're a team of 9 mathematician stroke analyst types. So we're a mix of computer scientists, mathematicians, business analysts. And what we are is, I don't know if the phrase operations research is used in the UK, in Italy, but management science maybe. We're just a group of analysts, and we're problem and industry independent. So what we aim is to find the problem and solve it through some sort of mathematical analytical approach, rather than just being a supply chain analytical company, or rather than looking specifically at a particular industry sector, such as asset management. So that means that that within this domain, if you imagine what we tend to end up doing, is the development of bespoke decision support solutions, as very similar to the tool that we saw produced for GSK. And our two main approaches for that are mathematical optimization, okay, I might be losing some people here at this point, and business simulation, okay. And within business simulation, we would use the AnyLogic tool as our primary simulation language. Now, because we're industry independent and problem independent, and we see that as a great value to our company, we've worked across many different industries, across many different types of problems, and across many layers of the business, from the strategic right down to the tactical. And our unique advantage is that we can do something, or we can come across a process that perhaps works really well for Rolls-Royce, spares part asset availability forecasting. So they're at the cutting edge of asset availability and the reliability forecasting of hierarchical machines. And we might be able to take it down to UK Power Networks, which has got similar problems, but not necessarily the reliability engineering experience of a large company such as Rolls-Royce. So where we approach simulation and business analytics is to kind of learn an expertise in one area and then see how it can be applied to the range of different problems that we're thrown at. And you can see we've got a section of cross-section This particular problem pervades the whole of REME. So the problem where they say that REME Aviation we're working too hard and the management think they're working too little, pervades the whole of REME Aviation. Now this project focused on one particular case study within REME, and it's not coming across very clear on the projector, unfortunately, but this is the Apache attack helicopter. So this is the really nasty helicopter, or really tactical response helicopter that you will see regularly as used in Afghanistan and other areas of intense conflict. So that's the thing with the big guns at the front, which is very intimidating if you're in the line of fire, I imagine, that fires its rockets and can do a lot of damage. Now specifically, this helicopter has some interesting characteristics. It has a very poor availability record. Very big political problem in the UK. Okay, it makes the press a lot. So our troops in the UK, if they are subject to attack, one of the key things that people like to look at is, was a Apache helicopter available to support the troops at that point in time? Now, when it's not available, the first thing that the press do is criticise the UK government for not having enough money to buy enough Apache helicopters. We don't have a lot of these things, actually. And if you look at what the US forces have got, they've got hundreds of these things scattered everywhere. Okay. The UK MOD, the political argument, which they never managed to make successfully in the press, is that we don't need as many as the US. The US solves its availability problem by buying a lot of them. They've got a lot of dollars. If there's a problem, if they don't have enough in service, they will buy 10 more. Boeing will do them a deal, they'll get 10 more, and away the problem goes. That doesn't actually address some of these issues and the complexities that this may cause. So in the UK at least, for every 1 hour this thing flies, okay, so an average mission is about an hour and a half maybe. For every 1 hour that this thing is in the air, you've got 35 maintenance hours to achieve that 1 hour. Now that sounds like a staggering statistic. From my perspective, at least, when I started this project, I was like, wow, are you sure? So how on earth can 1 hour flying generate 35 hours of maintenance? And in particular, the maintenance is a little bit skewed, but it's comprised of 3 main areas. So before a helicopter goes out, there's a preparation phase. Okay, so the helicopter has to have the right air filters fitted on the engine, it must have the right weapons attached to it, it must have the correct configuration of the instruments depending on the climatic conditions that it might be facing today. When it's out on deployment, so when it's in Afghanistan, let's say, it's going to do daily missions. Now those daily missions are going to generate the need for maintenance. Yep, there might be maintenance that's scheduled on a cycle, there might be maintenance that's scheduled on a calendar basis, and of course there can be stochastic or random failures of parts within that helicopter. So the helicopter is a very complex device. Clearly it's got hundreds of thousands of components within it. On the critical ones, we might have some stochastic behaviour due to the flying of the helicopter that might lead to a failure. Something may break on it. The landing gear may not come down, the rotors may start shaking a little bit, there may be some aspect that require maintenance. And then, whilst you're in Afghanistan, what you don't do is any of the big work. Yeah? You might give the engine an oil filter whilst you're in the middle of the desert, but you don't strip it down completely and clean out every single part. So as soon as the deployment is finished, there's a recovery phase that is required in order to bring that helicopter back up to a certain level of standard so that it can sit essentially in a warehouse waiting for its next deployment. So the maintenance aspect of this helicopter is incredibly complex, made of a variety of different phases. The total maintenance burden is particularly high, and it's got a poor availability record. All in the context, now imagine the political decision, all in the context of REME being blamed for the poor availability, whilst also being asked to cut staff. Okay, so we've got this complicated problem with the bosses saying, you're overstaffed, you're overstaffed. With REME saying, no we're not, we're understaffed, we're understaffed. And all the time with the political decision saying, get more helicopter availability please, get more helicopter availability please. So a really complex system that we were tasked to look at. And that is, that's the context for our customer. And I have to state, I guess, that this, the UK MOD is a little bit forward-thinking, not amazingly forward-thinking, but a little bit forward-thinking. So this isn't a new problem, okay? And what they did was commission a piece of research work to investigate whether or not there were new approaches that could be used to address this problem. So one of the new approaches might be the concept of a bit of agent-based modelling. And of course it's a funded piece of research, but it is a piece of research. So what I will demonstrate today is the concept demonstrator rather than the production tool. So what I'm worried about is it doesn't look as nice as Luigi's demonstration, but we will see. So if we go back to the original concept, I don't know if anybody's heard the phrase lies, damned lies and statistics. Yeah, the quote attributed to Disraeli might be Mark Twain, somewhere in between. But this is essentially the cause of some of the issues that we see here. And we wanted to kind of get to the bottom of that. If you start to look at the management information that was currently collected by both sides, okay, both sets of data were correct. REME is overstaffed when you look at the aggregate level. When you're there working on the ground, if you look at inter-day utilisation, it can be quite low. If you look at peak utilisation, it can be very high. So you've got this concept where the both views are correct. Now, getting to the root cause of that was difficult to do. So you imagine you've got two generals sitting in a room. Okay, they've both got a budget. One's got the budget for REME itself, managing it day to day, and one's been told to cut 20%. Now, they've both got data there to support their views. They are both generals. They're not going to give in to the other one. REME general isn't going to allow any budget cut, and the other guy is going to drive that budget cut down. So why am I making that point? I guess I'm making that point because the visibility of what was happening within the problem was the key to the build of the simulation. Yeah? We could probably surmise by looking at the data that if you've got peak utilisation of staff at a really high level but a low level of aggregate utilisation, you might be looking at a system full of peaks and troughs. Yeah? That becomes evident when you start to look at the data, if you start to think through the problem. But when you've only got Excel and you've got to make your case to some senior like one star or chief of staff to the government, if you've got data that backs it up, and this is where the statistics point comes in, both points of view are backed up by data. We need a way in order to understand the problem in more detail so that you can make a clear and concise and evidence-based decision. And that is where the use of simulation came in on this one. So the requirement that was set for us was to deliver a more robust and visible, okay, approach to determine the REME establishment. REME establishment means the number of people who work within that organisation. It must be able to determine the number of staff that are required to go on each deployment, and a deployment could be 10 helicopters to North Africa, could be 20 helicopters to Afghanistan. That's what a deployment means. From the REME side, they wanted contractors. They wanted the ability to use contractors to supplement their staff. This is where we came with the workforce planning aspect. So remember, it's a workforce planning problem. We want the ability to add in contractors. Okay, that's counter to the argument where the top brass want to reduce the numbers. So they needed a good way in which they could show that the use of targeted contractors could improve the overall availability of helicopters. And this, I guess this comes. This is where AnyLogic really came into its own. Really, I think, Andre, you had a slide that talked about the person, and perhaps we should start with big data. We should start to consider the use of the individual. Now, any system is affected by the performance of the human. Okay, we're integral in all systems that we study, and in traditional simulation, discrete event or systems dynamics, we tend to ignore or forget the complexity of the individual. So I'm an individual. Today I might be having a good day because I slept really well last night. I didn't have any beers because I was too late to my hotel. I got up this morning, it's a Monday, and I've had a nice weekend, so my efficiency might be quite high. Okay. On another day, when I've been overworked, Luigi's been pestering me on the email, I've had clients telling me that the model's not working correctly today, I might be demotivated and therefore less efficient. Now, in certain circumstances in a human system, factors like that could very much affect the performance of the overall system. And one of the areas they wanted us to investigate, part of the reason that this was a research piece, was to see to what extent we can incorporate human factors into this manpower model. So I think you will probably be getting into the swing of this by now, hopefully. There's 3 areas of complex behaviour within this system. Firstly, we've got the deployment. It could be on the back of a ship, it could be in the middle of a dust-filled desert, it could be at the Queen's Garden Party in the UK, it could be an air-sea rescue off the coast. There's a myriad of different ways in which the deployments will happen. Now, critically, this is very significant. Okay? If you're on the back of the ship, there's a lot of salt. Yeah? Salt affects the deterioration of parts in the engine and other areas, dramatically different than if you're serving at a temperate North European environment. Yeah? There's also concepts such as hot and high. So if you're in a desert that's very dusty, that's very high, North Africa for example, your engine is going to wear very differently. So there's a lot of uncertainty around what the deployment might be over the next 5 years. So remember, we're simulating over the next 5 years. Then we add in the helicopter itself. So the helicopter is if we break it down, we can say that the helicopter is composed of 15 subsystems. Okay, weapon systems, engine systems, electrical systems, mechanical bits and pieces. All of those have stochastic deterioration in condition. So forgive me for going down the asset deterioration or the condition deterioration aspect, but if you imagine that this pen and this pen, although identical, will not wear out at the same rate. Yeah? The ink usage will be a little bit different to that usage. I will be using it differently to the way that Luigi is using his pen. So there's 2 levels of uncertainty that affect how these pens are going to deteriorate, or how when these pens will fail. Now, if you stick that concept into a helicopter, which might be comprised of 15,000 rotating parts, which wear differentially, so wear out differently, using something maybe like a Weibull curve. I can see people going, what on earth is the crazy English man talking about now? But a statistical approach to reliability. And if we consider that that helicopter could, for 6 months of the year, be used in a dusty desert, come back, and then go out to the back of a ship 3 months later, we've got a lot of complex behaviour going off with that helicopter. And then the final thing is the people. Okay? So we touched on this earlier. So if at the top level it takes 35 hours of maintenance on average to achieve 1 hour of flying, we now know that this helicopter is going to be used in a variable way. Okay, so we've got some uncertainty there. And then we've got this concept of it takes 35 hours. Well, 35 hours is okay, but let's say these guys have been in Afghanistan for 4 months, so a standard tour of duty is 6 months. They've been there every day for 14 hours a day, fixing helicopters after some very intense action. Do we think that they will still be operating at the same level of efficiency they were on day 102 as they were on day 1? Okay. I might think that their efficiency has decreased, yeah, because they may be stressed. They're missing their wives and children, okay? They've been working very hard, they're sleep deprived, they're fed up of being shot at, they're fed up of the constant barracking. There's a lot of areas. However, counter to that is the fact that they've been there doing this job for 4 months now. When they got there on day 0, they wouldn't have had the level of experience that they now had. Yeah, so you've built up a level of experience. You've got used to what it's like to turn a spanner in the dark in the dust. You've found a way in order to make your job quicker, your way of life easier. So we've got two counteracting aspects here, experience and stress, which might affect the efficiency of the individual. So again, another complex area which is influencing the overall performance of REME aviation. Now typically, in a simulation world, this is the real world, we might say, well, let's simplify out much of that complexity. Let's simplify much of that away and go back to the aggregates, because we can't handle that complexity. And the point of using, for me, the point of using AnyLogic, and the point of what my consultancy aims to do, is that we don't need to simplify out all of this complexity. What we do is use the agent-based mindset. We do simplify the problem, and one of the great things about agent-based modelling is that it forces you to start at the problem from the opposite side. So people tend to be reductionists, so we always observe the system from the top, and we presume that we can capture everything, and we presume that everything is modelable, and the results are deterministic almost. In an agent-based philosophy, you start at the opposite end. So you start with the things that are within your system that start to influence the performance. And really, you don't really know how your system is going to work at the end. What you're doing is isolating the areas that have an influence and capturing their behaviour. Now, what that means is that you get away from the complexity, or you break the complexity down into individual building blocks. So we've talked around, if we look at this from the top down, yes, it's very, very complex. But if we forget about the rest of the system, and if we just focus on the people and how they improve their efficiency through experience, and efficiency decreases with stress, we might be able to meet people in the UK MOD with human factors experience that know a lot about this, and it might actually be very easy to model that. Yeah? And so that's what we're going to do within this AnyLogic model. And AnyLogic is, for me, the only tool that allows us to do that. So we will break that down, we'll look at that bit. We'll just develop a model of the person. Then we will look at the helicopter, and we'll speak to some engineers, and we'll learn a bit about reliability, and we'll just create a model of a helicopter. Then we will talk to the guys who do the scheduling and know a bit about the deployments, and start to ask questions around how salt affects the deterioration of the aircraft, or what happens on a deployment to affect the individuals. So our problem actually becomes very simple in its isolated buckets. Top level, it's still very complex. Break it down a little bit, and hopefully it becomes somewhat easier. Not easy, but easier. Now, okay, obviously when you start to add all these things together, you get significant uncertainty. Okay, you couldn't address this problem in Excel. It's not solvable. You can't just look at this in Excel and start to use the averages, and that's where this whole problem, this system, has been going wrong. Simplistic approaches to this haven't worked. They've studied bits of this in isolation, yes. People do know a bit about experience, efficiency and stress. They've done some modelling on that. They've got an SD model, systems dynamics model, that looks to address or understand that. But there's never been an opportunity to combine it with what else is known about the aircraft. The aircraft goes through a lot of simulation. People know a lot about the aircraft. So again, the whole use of AnyLogic allows us to bring this thing back together. So the solution looks, again, at the top down, our rich picture looks excessively complicated. But remember that it's built from building blocks. So each building block is actually quite straightforward. So I will attempt a demonstration. And this will test whether or not I've achieved one of the main objectives, was to make a user interface that explained the problem to a group of people who wouldn't have experienced this before. Because remember, this model is going to be used to get our Secretary of State for Defence in the same room with the Chief of Staff for Defence, in the same room with my two generals, to explain what is the problem with helicopter availability, and why we can't take 20% of the staff out of Reading Aviation. So I've got to, hopefully you lot just at least don't tell me it's completely crap, otherwise I'll have to start again. But, so Wattisham is our base. So this is our main operating base. And then around the side, around the edge here, we've got all the operating sites, the forward operating sites, where our helicopters might go in a 5-year period. So this is we kind of have a plan about where they're going to go, although when they go and how long they go for is not deterministic. So this is the sites that they may go and operate in, and this is data driven, so we can add in any number of sites around this. So Operation Herrick, X-Crimson Eagle down here, these are different geographic locations. So note that I've not gone for a geographically accurate representation here. There was no value in doing it geographically accurate. We've seen some very nice GIS stuff. Yes, we could have used that within AnyLogic, but the purpose here was to try and illustrate what's happening within the model. So the red here are the people, and the grey are the helicopters. So this is the point at which everybody either falls asleep or walks out the room. So when I start to run this model, what we will hopefully see is that time is continuing, going very slowly. I think I need to get some action going here. Now, hold on, let me just pause. Ooh. Right, so down here, this site, according to the data, has specified that it wants 3 helicopters. Okay, so we're going to simulate this deployment cycle over time. So these 3 helicopters at some point need to go to embarked, okay, which is an on-sea deployment, I believe. So these have now entered the deployment. These have now entered the preparation phase. So remember that of our 35 person hours for the maintenance, we will start to see that these helicopters, as is shown by the black lines, require people in order to do that maintenance. Okay, so quite straightforward. This model builds slowly in its complexity to try and make it accessible. So we're going to get these helicopters ready. So now we're fitting air filters, now we're fitting the correct weapons, now we're preparing the instruments. Okay, at some point very soon, hopefully, our helicopters will deploy to site. Let's run it at full speed. So we'll see that this preparation phase takes time. And you're right, look, utilisation of all the rest of the staff is really, really, really low. Okay, let me just pause. Okay, so what's happened now is that as these helicopters deployed, okay, they robbed a number of staff from the main operating base. So this is typical of how it works, yeah? Helicopters go and they take people with them in order to do the daily maintenance that happens on a helicopter. So our 3 helicopters deployed, they took, I don't know, 100 people with them, and now these are going to go out on daily operations, and these 100 people are going to be there in order to facilitate the daily repair. Okay, what we have left are all the people that are still here, along with all the helicopters. But now also we've got a second deployment going off at Pashton Panther with 2 helicopters and let's say 75 people. So whilst at the same time we've got UK training trying to take 2 helicopters over here. So we start to see this pattern of preparation work requiring people within the main operating base at the same time as we're getting the complexity of deployments going out to each facility, to each site, and all these helicopters will require a certain maintenance tasks during their daily operations. So remember, what we've managed to see so far is deployment, is preparation and deployment. So now you'll see that more people are moving to the UK training site. We'll see we've got lots of work going off at Embarked with lots of flying. So you can't really see the helicopters changing colour, but they're changing colour to show that activities are happening. The black lines illustrate when there's work happening within these individuals. Now what becomes clear, and now we've got people and helicopters moving back, and as helicopters arrive back, you'll see that there's a sudden burst in activity to recover these helicopters back to some level of availability. So we've still got this activity going on here. Richard Martin's just come online, if anybody wants to speak to Richard Martin. Okay. And we've got lots of activity. Now we still haven't got all the people back yet because they're here. Now if we're just watching this chart, you'll see that really these guys are sitting around kicking the heels, aren't they? Yeah, people are actually going out on deployment for a rest. And anecdotally, that was one of the first things that they said to us. People go on deployment for a rest because it's a lot less intense than what happens at Wattisham. So now we'll see that when these helicopters return, okay, there's a lot of maintenance that's going to be required on this helicopter because it's been doing a lot of flying. When it goes back, we're going to see a burst of activity to recover these helicopters back up to some level of maintenance. Okay. Now, purely, the illustration was exceptionally powerful. So the first time we demonstrated this to the client was only kind of 3 weeks ago. And we've got the two generals that we knew and a person who was there as an independent kind of quality control person. And they stood back in amazement and they said, wow, that's the first time that we've ever seen our problem so clearly illustrated on screen. So what you can see is the peak and trough nature of the work at REMI. And so you can see that from the black line, so the sudden intense burst of activities when helicopters come back. That just shows you how REMI operates. Okay, it's got lots of steady state work to do, but all of a sudden there's these intense bursts of activity. And you can also see the problem with too many people going out on detachments. So we saw that this embarked took a lot of people, took about 150 people, and that's based on their current planning rules. Now what that is doing is robbing staff from the main operating site. Okay, they're not having to do a lot of work because there's a lot of people there, but the main operating site is now having to do all the work with fewer staff, with the potential for a lot of uncertainty about when helicopters are returning. So in reality, you can actually fully explain why you've got those lies, dumb lies and statistics problems, because it's illustrated. Both people are correct. The system is overworked at times, and yes, the system is overmanned. Yeah? There's too many people there at times for the work that they need to do. However, you immediately can visualize what's happening on the screen with that. I mean, that must be an intense 2 weeks. When you get 3 helicopters, or you might have 10 helicopters coming back at the same time, you don't know what the next deployment will be, so the pressure is on to get those helicopters there. If you've already sent 500 of your people out to Afghanistan, the people who are left at the base are going to be working very, very, very hard indeed. So, I mean, we're clearly there in terms of illustrating what is happening. If we speed this a little bit, but of course we want to get some statistics in order to back up our case as well. So if we start to have a look at the statistics that we're collecting for here, and first of all, we've got an indication of how many people we have in our system, and we can see we've got the concept of contractors that are planned and emergency contractors. So we're already giving the people the facility to see how contractors influence the system. Emergency contractors are the ones that you wake up at 8 o'clock in the morning, you're the first one in and you realise that there's only 2 people there and 15 helicopters in front of you, so you pick up the phone and you pay top dollar to get 50 people there that day in order to facilitate the work. So then you've got emergency contractors, which this system allows you to see. We're splitting that by the 2 trades, avionics and mechanical, aircraft and avionics. And we can see where we've got planned contractors and the use of emergency contractors. Okay, but really what we wanted to get into is we wanted to consider those human factors aspects as well. So there's a warm-up period, so the charts look a bit silly at the moment. But what we're starting to see here is the interplay between the average level of stress for a REMI member of staff versus the average level of experience for a REMI member of staff. Now there's an SD model that includes more factors than just stress and experience, so it's all to do with the complexity and intensity of the deployment as well, but we're summarising it down here to have a look at what that means in the efficiency aspects of the staff as well. So we're trying to get back to this concept that a job will take longer if you're less efficient. Okay, so we're bringing in that complexity around in this loop as well. So we've got the complexity of the helicopter, the complexity of the individual, the complexity of the deployment, and the complexity that if you're working people too hard, stress might be increasing at the same rate that experience is increasing, but that could be having a detrimental effect on efficiency, which is actually coming down in this environment. Yeah, and we can add in new staff as well. So the minute you take on new staff, you've got lower levels of experience, which might be influencing the overall efficiency of the operation as well. And of course, we can just keep on collecting statistics in order to prove the case. So the number of aircraft, the utilisation of the staff, and we could see, look, okay, we can start to see what's going on now. Look, we've probably got average utilisation hovering around, what, 0.5, 0.4, something like that, but we've got peaks where it's up to 1 on a regular basis. So if you're working in that 6-month period, you might be thinking that you're quite stressed out. If these peaks start to combine, you're going to be having a very busy couple of weeks indeed. Okay, so that's my demonstration. I hope it makes sense. It's maybe a complex subject to try and get across in 10 minutes, but hopefully you can see what we've done within the model. The benefits, I really do have a very, very, very happy customer. I very rarely saw a team from both sides, both from REME Aviation and from the staffing department, so the managerial wing of the MOD, so happy that they had a decision support tool that illustrated the complexity of their problem from all perspectives. So we've got the complexity of the helicopter, we've got the complexity of the individual, we've got the complexity of the deployment, and we've got the interplay between them, so how they were influencing each other. If we go back a year, this project was competed against the manufacturer of the helicopter. So one of the things, so this was an open competition that said, can industry find a way in which the UK MOD can get 20%, in fact they were after 15% better availability for its helicopter fleet. So that was the question, and the idea was that industry, myself included, would come up with novel ways in which we could do that. So it wasn't simulation versus another simulation company versus another simulation company. We could just propose whatever we liked, and then they decided with their 1 million budget that they got to spend on this, who got the money, okay? So we competed against the like of Augusta Westland and BAE Systems, and they were all looking at technological research projects about how you could get better availability of your helicopters. So they were talking of next generation research into the next generation of ridiculously expensive, hard to find metals that would allow the helicopter to go longer between service intervals when it's in the front line. And they were talking of spending kind of 5 to 10 million quids just in research around the next engineering solution to this problem. Now, as we demonstrated with this, and this model was complicated, but I mean it was completed within 3 months. It didn't cost £5 million to develop this model, nowhere near that, much less than a tenth of that. And we were able to demonstrate that no, sometimes the problem isn't an engineering solution. Okay, we spend a lot of money trying to fix the problem through mechanisation and engineering, whereas in reality, the problem is that it's a human-based system, a human-based system of interconnected complexity. When you start to address that, and we demonstrated through simulation how that could be addressed, you get the same level of savings for absolutely no investment here. You know, now we've done this and demonstrated how best to coordinate the system, they should be able to achieve their 20% improvement beyond their target without spending 15, 20 million quid in the next piece of technology that will enable the helicopter to fly longer, faster, further for lower maintenance, which is where all the engineering solutions came from. So, I've probably overstayed my time, sorry Luigi, but I can take questions now, or again we can leave them to the panel session, such as Luigi suggested.